Okay, excellent. It looks like it's recording. Let's zoom in a little bit on the screen. Scoochie this over to the side. So if you can kindly be aware of the camera, that would be appreciated. So I'm going to be recording this and putting it up, posting it online. I can post it in both the online 102 and the 102 brick and mortar course, so that people who aren't here have access to it. Does anybody need a review packet? So, awesome. So, and I'll also post a copy of this online after this today. So this is just to get us started, give us a little topic to focus around, and then after we go through all these questions, we can take a moment and cover any additional questions that you have. Let me see. I don't have because it's so late in the day, I don't have a cameraman, so kind of trying to make sure that you can actually see the screen and the camera. Okay, so the very first question, now these are in the order of the units that we did. So the first unit is the meteorology unit, the second unit is the astronomy unit, then we did Earth's interior and minerals, and then we did, as our last unit, superficial processes, including rivers, glaciers, deserts, all those things. And a lot of stuff on soil formation, weathering, and erosion. So, first question, is the unlabeled graph below pressure or temperature with altitude?
Temperature.
Temperature. Okay, so you think that it is temperature. Now, why do you think that it is temperature?
Because pressure changes continuously, temperature, it falls, then it rises, then it falls and rises in the different layers of the atmosphere.
Excellent. So temperature changes with altitude. Pressure always declines. So if I was going to draw a pressure plot on top of that, Barb's got it. How does it look?
Go off.
Yeah, go off. It exponentially decreases as we go off. So this is temperature. And if I was going to add a line called pressure, let's see if I have a colored pencil in here. Here's my colored. Oh, nope. I'll just use the red pen. If I'm going to do pressure. This plot looks like this would be pressure. Now, I should name the layers in the graph. What's this bottommost layer called? From 0 to about 12 kilometers.
Troposphere.
Excellent. This bottom layer is the troposphere. Now, this is something I saw in both classes where people labeled this line as troposphere. That's not correct. It's this zone in here is troposphere. This line here has actually got a name called the tropopause. It's the boundary between the troposphere and the next layer above it. So what's this layer called?
Stratosphere.
Stratosphere. And what important process or important thing is in the stratosphere?
Where ozone is.
Excellent. The stratosphere is where the ozone layer is. Now what's this next layer called?
Mesosphere.
Mesosphere. And the top layer?
Thermosphere.
Thermosphere. Excellent. Now, second question, define theory and hypothesis. And we'll just give 2 examples of a theory. In fact, we'll give more than 2 examples. We'll give a whole bunch of examples of theories. So what's a theory and how is it different from a hypothesis? Yes, Barb?
A theory is basically a statement or a fact that's been proven over and over, resulting with the same results each time it's been tested.
Excellent. So a theory is a complex body of ideas that have been tested again and again and always shown to be correct. So let's think of some example theories.
Theory of relativity.
Theory of relativity. Theory of relativity, and we'll talk about why the world is round. Now, the world is round is a good idea, but that's a simple fact because it's easily observable. It's not a complex body of knowledge that allows us to do future predictions. So what's another theory?
Plate tectonics.
Plate tectonics, excellent. Any others? What's a classic one? The one that a lot of people politically, in this country at least, have a problem with.
The Big Bang Theory.
That's
No,
one of them.
Global warming, probably. Right?
Global, that's another one, Big Bang. Global warming. What else?
Evolution.
Evolution, excellent, Craig, that's a good one. One that people don't have a problem with is atomic theory. The idea that everything is made of atoms is actually a theory. So, just as a heads up, you shouldn't eat in here.
Oh, sorry.
That's okay, I know you're from the online class, so how would you possibly know that? But you kept going for him and it's like, but there's lead and animal poop in
I'm
here and
sorry.
you don't want to
I
eat in
know.
here. No, it's cool, it happens. So, atomic theory, so the theory that everything's made up of atoms, gravity, this idea that when I drop a pencil, that's the same force as makes the planets go around the sun. All of these are theories. The important thing here is that scientists treat theories as facts, as true. Now, what's a hypothesis?
Educated guess.
Excellent. A hypothesis is an educated guess. For a hypothesis, it may or may not be true. It gets confusing for a lot of people who watch the news because the news does a very, very bad job of distinguishing frontier science, which is grounded in hypotheses, and actual theory. Okay, so for example, they'll be like, chocolate is good, and then the next week chocolate is bad, and then milk is good, and then milk is bad. That's all frontier science. That's all working off of hypotheses and doing different tests And it's not until many, many years when there's a large body of evidence that we can actually build theories off of those individual studies. Actually, John Oliver, the comedian, did an excellent episode on the idea of the difference between theory and hypothesis, and testing the whole idea of, science in the news and that sort of thing. So Google John Oliver science to find that episode. It's actually very good. Foul language, but good. Because he's a comedian. Okay, moving forward. If the Earth had no tilt, would it still be cold at the poles and warm at the equator?
Yes.
Yes. What would change? Seasons. There would be no seasons. Why?
It would be cold at the poles still because the energy from the sun doesn't directly hit the poles like it does the equator.
Exactly. So the key here is angle. Okay? This is the fundamental idea of why seasons happen and why it's cold at the poles and warm at the equators. It has nothing to do with distance. On the first exam in both classes, lots of people put down distance from the sun is what makes the poles cold, but that's wrong, okay? It's actually the angle. So let's actually go over that. We can use the flip side of this to discuss this as a review. So the Earth is more or less a sphere. It's round. And the sun's rays, the sun is so far away that the sun's rays arrive parallel to one another. Now, if you're standing here at A, at the equator, and you're a person, at noon, the sun will be directly overhead. So the equator is hot because the sun is high in the sky and the rays are more direct. However, at the poles, and I'll put B here at the North Pole and B here at the South Pole, a person standing at the poles sees the sun low in the sky, even at noon. It's at an angle, even at noon. Now this happens because the Earth is round. So it's the curve of the Earth that causes the angle of the sun to be lower at the poles than the equator. So this is why it is cold at the poles. Now let's go back and talk about the seasons. The seasons are caused by Earth's tilt. Around June, the northern hemisphere has more direct rays. And around December, the southern hemisphere has more direct rays. So it's the same diagram we just did, only we now have a tilt on the Earth. So the sun's rays are arriving this way. So where is it higher in the sky in this picture? In the north or in the southern hemisphere?
North.
In the northern hemisphere. So the sun's rays are higher in the sky, or the sun is higher in the sky in the northern hemisphere. So what season is this?
Summer in the north.
Summer in the north. Awesome. So number 4, draw a diagram showing how each state becomes the others. Include the following terms in your diagram: melting, freezing, evaporation, condensation, sublimation, and deposition. So what are the 3 major phases that are on the surface of Earth?
Solid, liquid, and gas.
Solid, liquid, and gas. Perfect. So if I go from a solid to a liquid, I am melting. If I go from a liquid to a solid, I am
Freezing.
liquid to a gas,
Evaporating.
gas to a liquid,
Condensation.
excellent, condensing, gas to a solid,
Deposition.
deposition, excellent, and a solid to a gas,
Sublimation.
sublimation. Perfect. Now, any question about any of those phases? No? Awesome. Let us keep moving. Draw a position of the sun and earth when it is in winter in Watertown. Be sure to clearly label the north and south poles. So how do I start?
Draw the sun.
Draw the sun. I'll draw the sun over here. Does it matter which side I draw the sun on?
No.
Nope. Now I'll draw the earth. Does the earth belong up here or down here, or where does it belong?
Straight to the side.
Straight to the side. Remember, they're in the same, we have the earth, the moon, all of those are traveling in this orbital plane. So we draw straight out. We draw an earth. Not to scale. Earth has 1/1,000,000th the volume of the sun. So very much not to scale. So how should I draw the axis now?
As I'm looking at it, the tilt's gonna go this way.
Gonna go this way, exactly. It's gonna be tilted away. So the northern hemisphere, or the North Pole, is tilted away from the sun. That's winter in Watertown. Perfect. Notice I labeled the North Pole, this little end of the stick, as the north, and this is the South Pole. This is not north, this is not south, okay? On the test, I saw some people doing north like this and south like that. That doesn't make any sense, okay? The North Pole is the tip of that axis. That's true north, and the tip of this axis is true south, okay? There's also magnetic north and magnetic south and blah, 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 but that's outside the scope of this course. Okay, draw the position of the moon, sun, and earth during a new first, full, and quarter, and third moon. Third quarter moon. Now, when I'm drawing this, I'm going to draw the sun. Does it matter which side I put the sun on? Not at all. But everything else is going to be determined by the side I put the sun on. Now, where should I draw earth?
Online with it.
On line with it. So here I have earth, and it helps to label it. I'll put an E for earth. Now where should my moon be? Should my moon be over here? No. Remember, the moon orbits the earth. Okay? So I'm going to draw my moon. There are 4 positions described here. It's these 4 positions. Now which side of the moon is lit up?
Side that's
Left
facing
side.
towards the sun.
Facing the sun. Excellent. So I divide each one of these in half. I can shade dark the one that's not facing the sun. Now if I'm standing on Earth and I'm looking up at the moon, does this look part bright, all dark? What side am I seeing from the Earth over here?
Well, that one's a full moon, the one you point.
Point it at, right, because what am I seeing?
All of it.
Yeah, the whole thing is a full moon.
Right, so it's all bright. So this guy is the full moon. What about this guy over here? What do I see?
See nothing.
Nothing.
Nothing. I see all dark. So it's all dark. Looking from the Earth up at the moon, I see it all dark. That's the new moon. Now, what direction does every object in the solar system revolve?
Counterclockwise.
Counterclockwise. Everything's moving counterclockwise. So, that'll help me figure out which one's third and which one's first. So is the bottom one first or third?
I would say first.
First. It's the first one after the new, then 1, 2, third moon, right? So this is the first, and this is the third. Because in each one of these we see half the moon lit up. Make sense? Awesome. Describe the nebular theory. The nebular theory explains the origins of what? So we'll talk about the nebular theory, and then we'll also talk about the Big Bang theory, because those are 2 that are likely to show up. So what's the nebular theory?
Solar system.
Excellent. So it's the origin of the solar system. So, describe it. What happens? What's step 1?
Loose dust and particles in the atmosphere that are pulled together by gravity.
Excellent. So we got loose dust and particles in space. What's that called?
Nebula.
Nebula. Excellent. So we start with a nebula. Which is a cloud of dust and gas. It contracts Why?
Gravity.
Gravity. Attracts due to gravity. And then what happens?
Heat.
Okay, so heat, the center heats up, forming the sun. Larger particles collide and accumulate gas. And that forms what?
Planets.
Planets. Excellent. So I'm just going to take a moment and see if I actually have the nebular. Nope, next question is about supernova on the next page. So we'll flip this over and talk about the Big Bang Theory. Because one of those two at least you'll have to write an essay on. Probably not both, but at least one of those two. So let's talk about, are you here for the review?
Yeah.
Okay, so let me grab you a packet. We've moved into astronomy review.
Okay, that's, and then there's
What's that?
the, extra credit.
Oh yeah, when you, for the final.
Oh, okay, okay.
So I'll do them all at once. So let's talk about Big Bang Theory. What does it explain?
Universe.
Excellent. Explains origin of the universe. Okay, now describe it. What happens?
Just remember it was a large hot mass and it expanded rapidly.
Right, well, is it a large hot mass?
I don't know.
I can't.
It's been a while.
It actually
You know, I
said,
think you crossed out like large on my answer or something like that, so it's just a mass or something.
yeah, it's a tiny, incredibly dense point. Okay, so the universe started from a very tiny, dense point with all matter inside it. And that exploded outwards. Now what's one line of evidence for it?
The universe is moving away, is like spreading out.
Excellent. How do we know the universe is expanding?
The red,
Red.
The redshift.
Redshift, excellent. Well, that's why we're in review. If we remembered everything, we wouldn't be in review class right now, would we? So, evidence. The redshift of distant galaxies implies the universe is expanding. This has everything to do with the Doppler effect. It doesn't cause the Doppler effect.
But it's the presence of
Right, so the reason that, so we have this redshift. Remember, red is long wavelength light. So what's going on is that as the galaxies are moving away from us, they appear redder than they really are. And that's what the redshift is, and that's how we know they're actually moving away. Have we ever been to a distant star? No. We've never been to a distant star, let alone a distant galaxy. So we've never been out there. How do we measure these distances? And it's from things like light and redshift. Makes sense? Any questions about this? Awesome. Let's talk about numero 8. Bats use echolocation to find their prey, such as mosquitoes. Echolocation uses sound waves bouncing off an object to determine their position and motion. If the mosquito is flying away from the bat, should it appear higher frequency to the bat or lower frequency? In your answer, include a description of the Doppler effect to help justify your answer. So we'll start off with that. What is the Doppler effect?
As items appear closer, they have a,
Blue.
Short wavelength is blue.
Short wavelength is blue.
and
Short wavelength, high frequency is blue. That's right. It's not really closer though.
appears.
Closer is getting mixed up with another idea, and I saw this on a whole heck of a lot of tests. It's not closer or
Moving
further.
towards or
No.
Moving towards or moving away. It's your direction. Doppler effect only comes into play when an object's moving. If an object's standing still, Doppler effect does not apply to that object, okay, unless you are moving. There has to be some relative motion between the two objects in order for Doppler effect to apply. If both of them are standing still, no Doppler effect, okay? So the Doppler effect says that objects moving away appear low frequency, and objects moving towards, which is the same as low wavelength or long wavelength, and objects moving towards us appear high frequency
That would be blue, right?
short wavelength, exactly. Also high pitch. So when Doppler effect only applies when that object is at a significant fraction of the speed of the wave that it's referring to. So for example, when we're talking about echolocation, we're talking about sound. When we're talking about things like stars, we're talking about light, because the universe is actually expanding faster than the speed of light, which sounds really bizarre because there's this rule that says nothing can move faster than the speed of light, but it's not the objects in the universe that are moving, it's the space between them that's increasing. Really, physics is some messed up rabbit hole Alice in Wonderland stuff sometimes. So what is it saying? What should our bat see? Our bat hear?
Right.
low, yeah, red, low.
Low frequency, okay. So if the mosquito is flying away, should be low frequency. Make sense? So what did Hubble discover about distant galaxies?
The red shift, right?
Right, he discovered the redshift. They appear redshifted. So how is this related to the Big Bang?
It means that the universe is still expanding, it's moving outward.
Excellent. Means the universe is expanding. And this implies Big Bang. This is the origin of the Big Bang Theory. It's Hubble's discovery. So what's a supernova? Supernova.
And it explodes.
Yeah, it's a big bada boom. It's the biggest explosion in the universe since the Big Bang. So a massive explosion of a star. So we remember what are the stages of a star. For what's the before it's even born, it is a
Is it a nebula?
It's a nebula. Excellent. Gravity contracts the nebula, it begins to heat up, and it becomes a
Protostar?
protostar. Excellent. So once it heats up, a nuclear reaction starts up, and the size of the star stabilizes, it enters what phase?
Main sequence?
Yeah.
Main sequence. It's now a main sequence star. Then as it begins to die, what happens?
Red.
Red giant. Now what happens during red giant's phase? One thing, it turns red. What's the other thing that happens?
Starts dying, the star starts dying.
It starts dying. And how does its shape change?
Doesn't the core expand?
Exactly. The whole thing starts expanding outward, okay, because it's exhausting its central fuel. That central fuel is shutting down, so the star starts using fuel in the outer radiative zone instead of just exclusively in the core. That basically causes the star to bloat, okay? It also becomes cooler. Not that necessarily that it's producing less energy, it's actually producing a tremendous amount of energy, but that amount of energy is spread out over a larger surface area. So the surface cools, it turns redder, and it's bigger. Now, when it starts running out of fuel, that force of the interior force of fusion turns off. Gravity starts pulling the star in, the star collapses. So if it's a little tiny star, what happens? If it's a not massive star, size we shouldn't talk about because that's inaccurate. If it's a not massive star, say less massive than the sun or up to 3 times the mass of the sun, what's going to happen?
Turns into
It's a
a white dwarf.
White dwarf. It collapses and becomes this tiny, tiny, bright white dwarf. This very small blue object called a white dwarf. Now, if it's a very massive star, what's going to happen?
It explodes, supernova.
It explodes. So after the fusion shuts off, the force of gravity pulls the outside of the star inward. That force inward causes a massive fusion reaction to start up in the center of the sun, or the star. Remember, that our sun is a star, and all stars are suns. So that fusion starts back up again. It causes a massive force. It's basically a giant atomic bomb. It forces outward again in this huge supernova explosion. Now, after the supernova's explosion, what 2 fates can occur? Or 3 fates?
Neutrons?
It can become a black hole. It can become a neutron star. So these are all possibilities once the star explodes, that it can actually become a black hole or a neutron star, super dense object. So, what determines if a star becomes a supernova?
Mass.
Mass. Mass is that determining factor. So what we're really talking about here is a giant nuclear bomb going off in the, it's pretty cool. Huge nuclear bomb. This is a question focused for the online students because they did a project on the Tonga Islands. Why do Tonga Islands experience deep focus earthquakes? We'll talk about this again, and it's relevant to all the students, but we focused on the Tonga Islands as an example location. So why do we see the Tonga Islands experience these deep focus earthquakes? Where's the only place where earthquakes can occur on the earth? What part of the earth? All students should know this.
Is it because they're on the converging plate?
It's on a convergent plate boundary, excellent. So what part of the earth experiences earthquakes? Only part that does. Only part that's rigid enough to. That's a huge hint. Lithosphere, excellent. So only lithosphere can create earthquakes. The other parts are too plastic. In other words, they're not rigid enough, okay? You have to have something shivering and breaking. That rigidity is necessary for earthquakes to form. So, you absolutely have it. It's on a convergent plate boundary. So Tonga Islands is on a convergent plate. Now how do I draw a diagram of a convergent plate boundary?
You have the lithosphere going on, they have the continental lithosphere is stable and the oceanic lithosphere is going down underneath the continental lithosphere.
Does that only just happen in oceanic continental collisions?
Probably not.
Probably not. Everyone should know this. Where is a brilliant example of where it's oceanic convergence? Everyone in this class should know it. You spent a lot of time there in this class.
You talking about like Panama?
Yep, Panama, Honduras, and Nicaragua. That whole region started as an oceanic plate. Same with the Lesser Antilles region, of which they focused on the Tonga Islands, brick and mortar focused on the Lesser Antilles, but same idea, oceanic convergence resulting in island arcs, and in the case of Panama, the buildup of sediment and the formation of the isthmus. So, we got a convergent plate boundary. Looks like this. This is lithosphere. This is lithosphere. This is the subducting plate. What's this layer under here called?
Anthosphere.
Asthenosphere.
There we go.
Okay, so we have earthquakes deep underground. Now, we didn't really, in the brick and mortar class, spend much time on deep underground earthquakes. We spent a lot more time on island formation. So, we can review that if we need to. So, draw a diagram of a divergent plate boundary. Clearly label the lithosphere and the asthenosphere. So show me with your hands. If your hands are the lithosphere, how should my hands be? Yeah, like moving away. They're positioned like this. Remember, the lithosphere is actually, and if you take GO 131, which I'm not saying most of you will, but some do. Some people go, oh, I've actually had like 3 GO majors out of my GO 102 so far, which is really pretty cool. Like, that makes me happy. What I'm interested in is my introductory classes. So, it actually is kind of swollen up in the middle. So if you actually draw it like a little steeple, that's perfectly fine too. And the reason for that is outside the scope of this class, but it's actually that the hot material under the asthenosphere is actually creating pressure, and the lithosphere is actually very thin here, whereas it's very thick and dense as it cools further from the divergent plate boundary. So here we have the divergent plate boundary, and what do we find at that point right there?
A Rift Valley,
It's a
Mid-ocean.
Mid-ocean ridge.
yeah.
So this whole region is a rift valley that will eventually open up into possibly an ocean basin, such as we see in the Atlantic Ocean. The Atlantic Ocean actually started very similarly to the Red Sea today. So this is the lithosphere, this is the lithosphere, and this is the asthenosphere. So, number 13, define each of the major rock types. Oh, let's take a moment. This is a convergent plate boundary, and then show me with your hands, how does a transform plate boundary move? Right, like this. If I'm looking down on top of it, it's sliding back and forth like this, either like this or like that.
It's going, how, explain that again?
Sliding back and forth. So if these are the two plates, like imagine California, okay? This is California, this is the rest of the continental United States. It's basically sliding like this across each one another. So, define each of the major rock types below. So, sedimentary rocks. How do they form?
Isn't it weathering? Through weathering?
Excellent. So formed from the byproducts of weathering. Igneous are the easiest ones, I think, to define. What's an igneous rock? Formed from what?
Melted.
Cool. It's
Melted
very-
rock. Excellent. So from cooled, melted rock. And what are the two names for melted rock?
Lava and magma.
Excellent. Lava and magma. Excellent. Which one's at the surface?
Lava,
Lava. Which one's at depth?
magma.
Magma. Excellent. And then metamorphic rocks?
Heat and pressure.
Heat and pressure. But not what?
Not melting.
There's no melting. There can be tiny, tiny amounts of melting, but if you have molten rock and that cools, you have an igneous rock, not a metamorphic rock. Excellent. We are trucking it. We are partially trucking it because I didn't include anything from this unit. I'll go over a couple of those on some of our blank pages. So what is a supercontinent? Give one example of a supercontinent.
Pangea.
Excellent. So Pangea is an example. So what is a supercontinent?
Where all the continents were together before
Together,
the,
surrounded by
before the
water.
plates separated.
Excellent. So when multiple continents join, due to plate tectonics. Now there's been more than one massive supercontinent. There's been Pangea, there's been Gondwana, there's been Rodinia. Gondwana was actually a precursor to Pangea that eventually slammed into Laurentia, which is what we're standing on. Laurentia would eventually become North America, and that formed Pangea. Rodinia is much older. It actually is about 600 million years old or older. Actually significantly older than 600 million years. It was a supercontinent that formed during the Proterozoic. And and there were probably supercontinents that predated that, but our records back that far are pretty bad. So, how are fossils used to provide evidence for plate tectonics?
Like, for example, like that there's animals in Africa and there's fossils in Africa and South America that are the same.
Excellent, so there's fossils in Africa and South America that are the same. What other important feature are those fossils? Are those fossil fish?
They're land fossils, aren't they?
Right, exactly. So terrestrial fossils of terrestrial organisms imply land masses were once connected because there is no other way for the animal to get there. For example, fossils in South America can often be found in Africa. Excellent. And let me just bring up the last set of short answer questions. So, I'm going to draw a diagram of a meandering stream. So a meandering stream is a stream with curves. Yes, we can start making real streams have curves jokes if anybody wants. So where are our point bars and where are our cut banks?
Cut banks would be on top, right?
Right, so is it
And it's erosion.
A or B?
A.
A is our cut bank. And B is our point bar. And that also applies here. This A, this outside of the curve, is our cut bank, and this inside part here is our point bar. So the cut bank is always opposite the point bar. That's an easier way to really look at it if you turn it this way. Cut bank's on one side, point bar is on the other. The point bar is on the inside of the curve, the cut bank's on the outside of the curve. Cut bank implies erosion or deposition.
Erosion.
Excellent, this is erosion, and point bar is deposition. So, examples of chemical weathering. What are some examples?
Oxidation.
Oxidation. Most common form of oxidation is what?
Rust.
Rust. Excellent. What else?
Acid.
Acid dissolution. And we see that very often in limestone. From rainwater. Excellent. Why is rainwater acidic?
Carbon dioxide.
Carbon dioxide. Perfect. Examples of physical weathering.
Unloading.
Excellent. So, physical weathering include unloading, what else? Frost wedging, which is why we see so many potholes in the North Country. What else?
Root wedging.
Root wedging. These are all good examples. What does it mean if a glacier is advancing or retreating?
Advancing is growing, expanding, and retreating means that they're shrinking.
Excellent. So advancing means growing. Retreating means shrinking. Does it have anything to do with the direction of flow?
No.
No.
No. Excellent. So that's all I really have for some jogging your memory on the different units type questions. Now I'm just going to open it up. We have an hour if you want it. Do you guys have any questions for me? Yes, Barb.
The hydraulic cycle, can you show the diagram for that, please?
So the hydraulic cycle, the diagram that is going to be on the test is the diagram, let me grab the notes. And if you're wondering why the room smells like mice, my room smells like mice, it is because my office mate runs the zoo technology program, and I came into my office this afternoon. It's always a surprise when you work with someone who works in zoo tech, and he had giant cages full of mice. So my office now smells like mice. So just noticed that as I moved in the back, it's like, oh, that's a little odd for a geology lab, but we share this room. So this is the diagram that you need. What you should be most concerned with is that you're able to label these. So why don't we go ahead and talk about these very quickly. One is what?
Deposition.
Deposition. 2 is?
Sublimation.
Sublimation. 3?
Condensation.
Condensation. 4?
Precipitation. Oh, no, 4. 4, that's evaporation.
Evaporation. Excellent. 5?
That's precipitation.
Precipitation.
Oh, yeah.
Yeah,
Precipitation.
Clouds to oceans is?
Precipitation.
Excellent. Glaciers to oceans.
Runoff.
Lakes to water vapor.
Evaporation.
Excellent. Water vapor to clouds again.
Condensation.
Condensation, clouds to anything.
Precipitation.
Precipitation. Excellent. And that's true over here. So this is evaporation, condensation, precipitation. The only one that's different is plants. What's this guy called?
Transpiration.
Transpiration. Excellent. Now, as water moves through soil to plants, or through
Infiltration.
soil to anything else, it's infiltration. And then the deep motion of groundwater is called
Percolation.
percolation. Excellent. Good job. What? I have no idea what's going on back there. I'm just leave that right there. Just leave that on the table. Leave it right there. So, good question, Barb. Good. Any other questions? If you have another one, go for it.
I just want to make sure the phases of the season diagram,
The phases of the seasons?
the season diagram that we have
That's the one we covered.
with the, that's.
Right. That's this guy
Just
over
wanna
here.
make sure. The word.
What question? This is without a doubt going to be on the final exam. No guessing, every GO 102, in fact, every GO 102 student, in every GO 102 class, and all my 110 students, and also I think my 132 students, that exam will be, that will definitely be on the exam. Why? Because if you don't know how the seasons work, that's a problem. You shouldn't graduate college and not be able to say, this is how the seasons work, this is how the phases of the moon work. Don't want to see you on, I guess it's not Jay Leno anymore, but one of those comedy programs where they ask people, how do the phases of the moon happen? That sort of thing.
I think you should stick to your review for the question.
Stick to my,
Yeah.
honestly, a lot,
I-
this is a pool of possible questions. So a huge percentage of the questions in the short answer will be drawn from this. I might not say winter in Watertown, I might say winter in Australia, or I might say summer in Australia, or something like that. But it will be, the questions will be very, very similar.
If it's summer in Australia, it would be the opposite axis, right?
If it's summer in Australia, okay, so if it's, summer in Australia is this guy.
Okay.
Because summer in Australia, the southern tip of the axis is pointed towards the sun. Winter in Australia is when it's switched. Good question.
I had a question, it was on the, there's a chart on the Jovian and terrestrial, planets.
Yes.
As far as like the period of, or the length of local day and local year, which one's faster or slower, I couldn't find that.
Okay, so that's in your book. And let's go to, we'll write it under Big Bang because it's part of the same unit. Okay, so Jovian versus terrestrial planet. So length of revolution. And that's the trip around the sun. Length of
That has rotation.
rotation. That's on its axis. So revolution is around the sun, rotation is on its axis, and then the year and the day. Okay? So we have Jovian and terrestrial. So let's quick review. What's a Jovian planet? Jupiter.
Jupiter, Saturn, Uranus, Neptune.
Excellent. So Jupiter, Saturn, Uranus, Neptune. Okay? Well, so those are the big gassy or icy planets. What about the terrestrial?
Mercury, Venus, Earth, and Mars.
Excellent. Mercury, Venus, Earth, and Mars, and those are the little rocky planets. So terrestrial planets are more dense, they're smaller. Jovian planets are larger, but they're less dense. Jovian, just because they're so huge, are also more massive. Now, length of the revolution around the sun. The Jovians are further from the sun, so it takes longer for it to go around the sun. So for the Jovian, it's long, and for the terrestrial, it's short. Now, a trip around the sun is also known as a what? One what? Local,
Trip around the sun.
yeah, one trip around the
Year,
sun.
it's a local year.
It's a year. So a Jovian year is
Long.
long, and a terrestrial year is
Short.
short. Excellent. So the length of the rotation, or the length of the period of the rotation. For a terrestrial, that's actually long. And for a Jovian, that tends to be short.
Why is that?
Why is that? That has to do with the imparted angular momentum. So why does everything go around the sun in the same direction? Why are all the rotations except for Venus in the same direction? So we'll take, or all the rotations except for Venus in the same direction. So we'll take Venus out of the mix for a minute and say everybody except Venus. The original spin was imparted on the planets and the solar system in the early nebula. So in the nebula that formed the solar system, that nebula was slowly rotating. So that the angular momentum, that circular motion from the original nebula was placed on the planets, and so they have an angular momentum and it's all in the same direction. Now, it's easier for Jovian planets to maintain their angular momentum than it is for the terrestrial planets. We're all gradually slowing down because most of us have things like moons, okay, which cause tidal locking. Also, tidal locking slow down. Basically, the pull of gravity is slowing down the rotation. For the terrestrial planets, because they have very little mass, that's much faster than it is for the Jovian planets, which have a whole lot of mass. It's the same idea that my little teeny tiny Chevy Spark, as long as it has snow tires in the winter, it stops on a dime. Whereas the Truckosaurus behind me, the giant, I don't know, Ford 4x4, roar, could eat my car, has a huge stopping distance, which, you know, never really thinks about because it just has so much more mass, okay? So because of the relative mass of Jovian versus terrestrial planets rotate much more slowly than Jovian planets because they've just been slowing down. The rate at which they slow down is much faster than the Jovian planets. So the Jovian planets still have lots of the remaining angular momentum. So, what's the length of the day then?
Shorter for a Jovian,
Shorter for a Jovian and,
longer for a terrestrial.
excellent, short for a Jovian and longer for a terrestrial. So like, for example, a Jupiter day is something like 10 hours. Which is pretty incredible. Yeah, it's pretty crazy. And despite its epic mass, the sun manages to complete one rotation in about a month. Yeah, because of its huge amount of mass and, I mean, in spite of its huge size, it manages to complete an actual full rotation in about a month. So, any other questions?
The permeability experiment that was on the question on the exam.
That doesn't have anything to do with you.
That's
So
right,
that
you
was,
just
yeah,
said
that was,
I
that,
apologize, yeah.
right, no problem. That accidentally, when I was modifying it from the Geo 110 people, they have to worry about their permeability experiment. You guys didn't have enough permeability experiments, so that's just a typo.
What is the name of the particle that light is made of? I know it's both a particle and a wave, but.
Right, and the particle is, anybody got it? Right, Bo? Second half of the
photon?
word, huh?
Is it photon or?
Yeah, it's photon.
Okay, I
It's just a
wasn't sure.
photon.
I see that. During an eclipse, we can see what part of the sun, the
Corona.
corona.
During an eclipse, you can see the corona.
If not, we could see the photosphere on a regular basis, right?
On the most of the time you see the photosphere, that's releasing most of the light that we see from the sun. The sun itself is millions of degrees, but the surface of the sun is only about 6,000 degrees Celsius. And that's the light produced from the photosphere's temperature. Yes?
What
What do you
rocks,
say?
what rocks should we really like concentrate on, like,
I gave my brick and mortar class that list. Not sure my online list has that list. So it's the original list that we had back.
Off the
over-
summary, right?
Yeah, not just the summary. Well, the summary, that's a good list to know because all of those rocks and minerals, and I'll post that list for, actually, we'll just go over that list very quickly here as well. And then 3 earth materials. Earth materials. There we go. So this list, 10 rocks, which showed up in the homework for online. You need to know granite, basalt, obsidian, sandstone, coal, limestone, rock salt, shale, marble, and gneiss. So I'm just gonna quiz you to see if you guys know those guys. So marble, which of the 3 major types of rock is marble?
Metamorphic.
Metamorphic, excellent. Which of the 3 major types of rock is rock salt?
Chemical.
Chemical what? Chemical, 3 major types. Sedimentary, perfect. Shale.
That's sedimentary.
That's sedimentary, excellent. Gneiss.
Metamorphic.
Metamorphic, excellent. Coal.
I know it's biochemical, or, no.
Organic what? Sedimentary, excellent. Granite.
Igneous.
Igneous. Obsidian.
Igneous.
Igneous. And basalt.
Igneous.
And limestone.
Sedimentary.
Yes, sedimentary, biochemical sedimentary. So you need to know granite, which is igneous, intrusive igneous, basalt, which is extrusive igneous, obsidian, which is extrusive igneous, sandstone, which is clastic sedimentary, coal, which is organic sedimentary, limestone, which is biochemical sedimentary, rock salt, which is chemical sedimentary, shale is clastic sedimentary, marble is metamorphic, and gneiss is metamorphic. Any other questions?
Transit.
Transit, that is when a planet passes, from our view, a planet passes between the sun or a star and us.
And that's how we know there's a planet there, right? It is.
Right, if it's a distant star, that's how we know a planet's there. It's also how we determined the original diameter of the solar system, but that's a little bit more in-depth calculation.
Can you repeat that? I'm sorry again.
So a transit is when a planet passes between us and the sun or a distant star and us. And that's from that article that you read on the Kepler program and understanding how we find other Earths.